third and final video on alcohol oxidation, we'll be thinking about how we can actually improve the Jones oxidation. One of the problems we'd like to address initially is this issue of over or double oxidation of primary alcohols. So maybe stated a different way, we could try to design a different reagent or modify the Jones oxidation in some way, where we could actually perform a single oxidation on a primary alcohol, like this one, where we would actually end up with an aldehyde rather than a carboxylic acid. So the crux of our problem is to know what types of reagents to use. So let's talk about some design principles here. So you can get a sense for how chemists might go about actually developing sets of reagents to do the reactions that we want them to do. Our design will start by thinking about where the problem is coming from, the problem we're trying to solve. So that's that the Jones oxidation conditions involve water. That water is what creates the hydrate, and then the hydrate gets oxidized to form the carboxylic acid. If I have no hydrate, I can't do that second oxidation. So we'll say hydrate formation. And then I want to think about, well, why would I have water in there in the first place? Water was required to dissolve the chromium trioxide. So when I look at this, it seems to me that if I want to keep chromium +6 as the electron poor piece that gets reduced and drives the chemistry that I want to do, I need a reagent that contains chromium +6 that is soluble in organic solvents. Right, the idea here is that these organic solvents, they're not going to contain water, or we can develop ones that don't need water in them. And that should help me. If I don't have any water, I can't make the hydrate, and I've solved my issue. To do this, I'll have to alter the structure of CrO3. I need to keep the chromium, and I'll probably need to keep at least one of those oxygen atoms so that I can make sure the chromium is at the +6 oxidation level. But I can play around with the other things attached to the chromium so that it lends itself to being dissolved in a slightly less polar solvent. What we actually end up coming up with is called pyridinium chlorochromate, or PCC, not Pasadena Community College, this reagent. So its structure will look a lot like CrO3, which probably is unsurprising. We'll have our chromium atom. We have two different oxygens to which the chromium is double bonded, an oxygen and a chlorine now, and this oxygen here is negatively charged, or one of the oxygens is going to carry a negative charge. The pyridinium is what's called a countercation, so this is a salt. Where we have a negatively charged ion that carries the chromium atom. But we know that negative charges don't really exist in isolation for the most part, and certainly not really in organic chemistry. So we need to have something that's positively charged. By using the so-called pyridinium ion, this one here, we actually have a ring that's organic, and it's this positively charged cation with this organic structure that's going to lend some solubility for the overall compound in solvents that are polar organic solvents. So rather than water, we could dissolve these things in things that we could use and exclude water from, and that will be helpful for us. So let's look at how we would do a PCC oxidation. Well, it would be as simple in our example case here of simply treating this with PCC. We notice that we're going from the C+1 oxidation level, so that's our alcohol here, C+1, to the C+2 level, and that means that we really only need one equivalent of PCC, which I'll abbreviate as 1-equiv. The concept here is that that chromium atom in one equivalent is reduced from Cr+6 to Cr+4, and that's going to correspond to oxidation of the carbon by one level. So if I'm adjusting carbon one level in one site in the molecule, I need like a mole of PCC for every mole of carbon that I'm oxidizing. If I had like two alcohols, for instance, and I wanted to oxidize both of them to aldehydes or ketones, for instance, I would need just as many equivalents of oxidizing agent, in this case PCC, as I would carbons that are being oxidized. So let's look at another example here, where we've now developed this concept of PCC. We know its structure. I don't need to memorize the structure. I just wanted to motivate why its structure solves the problem we set out to solve, this issue of being able to exclude water. And we'll look at another example involving PCC here. So let's look at a diol. It looks like this. And we want to oxidize this compound with PCC. I'm going to draw on all my blue hydrogens in order to make sure I can predict what's going to happen. PCC. And I want to do oxidation at two different places. I want to oxidize this carbon in the primary alcohol and this carbon at the secondary alcohol as many times as PCC will allow me to do. That looks like I should be able to oxidize the primary alcohol once, right? I don't form the hydrate, therefore I cannot make the carboxylic acid. I know then that our primary alcohol will become an aldehyde in this case, and one of those blue hydrogens will still be in the final product, the so-called aldehyde hydrogen. So that's carbon 1. Let's look at carbon 2 now. Well, can PCC oxidize secondary alcohols? I think so. Secondary alcohols are not too dissimilar from primary alcohols, and it turns out that that's true. PCC does oxidize secondary alcohols. Here there's really only one option. We're only able to do one oxidation because we've only got the one blue hydrogen. So we would expect to see oxidation of our secondary alcohol to a ketone. Make sure I follow that carbon correctly using my numbering system. So I see that carbon 1 is going from C+1 to C+2. There's our nice single oxidation now that we were setting out to try to achieve. And carbon 2, or secondary carbon, is going from the +1 level also to the +2 level. So the other thing we could think about is how many equivalents of PCC would we need to actually get this to work? It looks like I'm removing 1, 2 of those blue hydrogens, and that means I need 2 equivalents. The way we think about that is that we're changing 1, 2 oxidation levels in total. So I'll need twice as many molecules of PCC as I will molecules here. So in the last section of this video, we'll be talking about more modern kinds of oxidations and a different kind of a problem that we encounter with these chromium-based oxidants. Unfortunately, we've learned that chromium +6 is carcinogenic. What that means is that most compounds that contain chromium atoms at the +6 oxidation state will cause cancer when they're incorporated into a living organism. Even more tragically, we know that this is true for humans because there have been high-profile cases of small communities becoming cancer hotspots because of chromium +6 working its way into the town's water supply. There's a famous movie about this, Erin Brockovich, which is about a community in California that has its water supply poisoned by PGE dumping what's called chromium +6 or hexavalent chromium in their water supply. Obviously, organic chemists would like to try to mitigate our hazard associated with developing cancer doing our jobs, so we've developed other kinds of oxidation reactions that don't involve chromium +6, and even more recently that we call green or benign. These are things where the wastes that we generate aren't necessarily hazardous. In a lot of cases, they're compounds that we already find in nature in abundant quantities. There are lots of examples of these kinds of oxidations, certainly too many for us to talk about in this class. So I'll just pick one, the so-called bleach oxidation. So this kind of a reaction works with, well, we'll choose a simple alcohol to start, that of acetone. And what we're going to use is, maybe unsurprisingly, bleach or sodium hypochlorite, so NaOCl. Just as an aside, chemists like to pronounce all of these things phonetically, or at least some chemists do. So NaOCl could be NaOCl, which is kind of fun to say. And it turns out that this reaction needs to be run at a relatively low pH, so pH of about 4. Oftentimes we use acetic acid as either a solvent or a co-solvent for this reaction. And what we actually find when we do this is first that the alcohol in our substrate is oxidized effectively. Well, that's good. That's what we're trying to do. So just to reinforce this even more, our blue hydrogen is removed. But one of the things that we like about this is that byproducts are salt, NaCl, and water. So I'm pretty sure that water coming out of this reaction is not going to hurt us, and table salt won't hurt us either. Essentially what we're doing is taking an alcohol, oxidizing it using bleach, or the active ingredient of bleach, and we're getting ocean water back out as our waste. So this is really superior to our chromium +6 based oxidation reactions. The way that this actually ends up working is that the chlorine is getting reduced. There's a practice problem in the SLO where you work through this in a little bit more detail, which is worth thinking about. For our purposes, you can treat the bleach oxidation exactly as you would the PCC oxidation. And you're also welcome to just write bleach over reaction arrows rather than all of this set of conditions. Again, it's not important to me that you memorize every possible aspect of how you would run this reaction. It is equivalent to PCC. What I mean by that is that it does single oxidations. So if we have a primary alcohol, for instance, it's only going to do one oxidation, which is a little bit surprising because here we're generating water. You might think that the hydrate problem is going to persist, but for whatever reason, we find that that's not true. Bleach does selective single oxidations of primary and secondary alcohols. There is some selectivity differences between PCC and bleach in terms of whether they react faster with primary or secondary alcohols. We're not going to talk about that in this class, but again, if you're using outside resources, which again, I would encourage you to do if you find that it's helpful, you might encounter that. So please be clear that you will not be evaluated on whether bleach oxidizes primary or secondary alcohols selectively. The idea is that you would just know how many oxidations, like +1 to +2 versus +1 to +3, bleach would do, PCC would do, or Jones would do. So that concludes our video on alcohol oxidation reactions. We've talked about the Jones oxidation. We've talked about PCC and bleach as alternatives to the Jones oxidation. I just encourage you again not to try to memorize every possible permutation of these reagents and what they do. Focus more on organizing principles, for instance, using these blue hydrogens as a guide. And really it's the Jones oxidation that's the outlier. Even though that was the first reagent we talked about, it's really the one that does weird things, and that's only with primary alcohols. So you have like an exception to know and then a general framework to use for all of your oxidants. I would encourage you, along with the homework, to work practice problems in SLO number 3. So you can work with equivalencies. That's sometimes a sticking point for some students, and so you can really get good at correlating the structures of products, reactants, and reagents in these kinds of chemical reactions.